Ryan touched on this a little bit already, but let's go into a little bit more depth about activation functions and the ReLU activation function in particular. Now, the earliest neural networks just used a step function to decide what the output of a given neuron was given its inputs. So if the sum of the inputs into a given neuron were greater than 0, it would output a 1. Otherwise, if it was less than 0, it would output 0. Pretty simple. The problem is that we're using gradient descent when we're training a modern neural network. So when we're doing back propagation of the error back through our neural network, we're using the gradient descent algorithm to do that. But with a step function, there is no gradient. It's just this vertical wall at 0, right? So without that gradient, we have these mathematical problems that make it difficult to train a neural network. And for a while, this was seen as sort of a insurmountable problem in the field of artificial intelligence. But fortunately, we have new activation functions today that are deceptively simple, but solve that really big problem that we had back then. So some alternatives to the step function are the logistic or sigmoid function, and indeed we will use that in the case of binary classification like we mentioned. If you do have a binary output and you need to convert that into a probability, sigmoid is a perfectly good choice for that. There's also the hyperbolic tangent function, which is a little bit more smooth than a step function. There's also something called the exponential linear unit, which is a little more curvy than hyperbolic tangent, for lack of a better word. But the thing that people generally use these days is called ReLU, and that stands for rectified linear unit. And that's what this graph here is showing you. This is a ReLU activation function right here. So it's pretty simple. Basically, it's 0 if it's less than 0, and if it's greater than 0, it climbs up at a 45-degree angle. So it's just giving you the actual sum of the input weights as its output, if that output is greater than 0. Now, the advantage that ReLU has is that it's very simple, very easy, and very fast to compute. So if you're worried about converging quickly and about your computing resources, ReLU is a really good choice. Now, to be fair, there are variants of ReLU that work even better if you don't care as much about efficiency, and as computers get more powerful, that's becoming less and less of a concern. One is called leaky ReLU. So the idea there is that instead of being flat left of 0, it actually has a very small slope. And again, that's for mathematical purposes, to actually have an actual meaningful derivative there to work with, and that can provide even better convergence. There's also something called noisy ReLU, which can also help with convergence a little bit. But these days, ELU, the exponential linear unit, often produces even faster learning. And ELU is gaining popularity now that computing resources are becoming less and less of a concern, and now that you can actually do deep learning over a cluster of PCs on a network in the cloud. That's what activation functions are all about, but that's why we use ReLU. For the most part, it's quick and easy to compute, and it avoids all the mathematical problems that come with a step function. So it's usually a good starting choice for your activation functions within your deep neural network. Let's also talk about overfitting. So if you play around in the TensorFlow playground on this spiral pattern here, it's very easy to end up with these overfitting patterns here, where we have these like spikes, these tendrils that are creeping out just to try to overfit the data that we're given here. And just like any machine learning algorithm, overfitting is a concern with deep neural networks as well. In fact, it's sort of an insidious thing because it's so hard to visualize and understand what's going on inside of a deep neural network. So getting at the root of overfitting can often be a little bit tricky. And deep neural networks are especially prone to overfitting because you have thousands of weights to tune within these neural networks, and the connections between each neuron and each layer of your neurons can add up really quickly. So it's very easy for overfitting to happen. But fortunately, there are several ways to deal with it. One is just early stopping. So as soon as you see that your performance is starting to drop, that might be nature's way of telling you that it might be time for you to stop learning. If you start to see your accuracy as you're training your neural network start to level out, that might be nature's way of saying, hey, this is about as good as it's going to get. If I go further, I'm probably just overfitting. So very simple approach there. Just stop training your model once it starts to converge. There are also things called regularization terms, it's hard to say, that you can add to the cost function during training, and those are kind of like the bias terms that we talked about earlier. That can help too, but really the most common approach to avoiding overfitting is called dropout regularization. And the idea here is very simple and surprisingly effective. The idea is really just throwing away data as you train the network. And if you think about this, it's kind of similar to what we did with random forests, right? We actually withheld some of the attributes when we were training each individual decision tree in a random forest, because by withholding that information, it forced our model to try different ways of solving the same problem. And then when we averaged them together, we got a better result at the end. So it's a similar idea with dropout. Instead of withholding attributes, we're actually withholding neurons from our network at each training step. So the idea is to ignore, say, half of the neurons randomly at each training step. Pretend they don't exist at all. And the reason this works is because it forces your model to spread out its learning. If basically you're taking away half of its brain at each training step, you're going to force the remaining half of those neurons to do as much work as possible. And this prevents things where you have individual neurons taking on more of the work than they should. That's what leads to overfitting. And if you mess around in the TensorFlow playground, you could see examples where you had some neurons that were just barely being used at all. But by using dropout phases, that would have forced that neuron to have been used more effectively. So dropout is a very simple concept, but it's very effective in making sure that you're making full use of your neural network. And it's also effective at combating overfitting because it prevents any specific part of your neural network from taking on too much of the work. So it spreads out that distribution of the actual computation, which tends to prevent these spiky things a little bit. Now, implementing dropout in Keras is super easy, so let's dive into an example of that and see how dropout works in practice.